Welcome back. And here we go. Did a little work for us here. And what we have going on here is isohexanol in part VA. We can't do these two questions till we figure out what F and G are. Or sorry, until we figure out what F is. And we're going to make G. So reacting isohexanol with sulfuric acid and heat, that's a classic acid catalyzed dehydration. And that can be found in chapter 6. And the product molecule E will have a beta H missing and an alpha OH missing. There's your water. And when you're done, it looks like this. And VI is bromination and water. So VI part 1 would give this. The Markovnikov addition of the less electronegative Br and the less substituted carbon and the more electronegative O and the more substituted carbon. And then part 2 gets us to an acid-base reaction, which takes this H off, generating an oxide anion, O-, which then attacks the backside of this carbon to make an epoxide. Yeah, we have a new student coming. All right. So we have an epoxide, and in the other version, question 7, epoxides can also be made from alkenes. That's molecule E. Coincidence, it has the letter E and it's an alkene. It's reacting with a per acid to make an epoxide, same epoxide. And that's where we start question 8. And we're going to do sodium acetylide. That's part 1. Left off the spectator there. What that's going to do is attack the less hindered carbon. If you want to look at the mechanism, anion attacks the less hindered carbon. You get an O-. Step 2, hydrochloric acid protonates that. And we have molecule G right here. You get an O with an H. And 1 carbon over, you've got a C-triple-C attached to the less hindered carbon of the epoxide. Okay, and that is G. Now let's try it this way. Okay, the G is underneath. Okay. And we need a mechanism. Oh, we do need a mechanism for that. So why not start with that? Step 2 is HCl. Okay, my computer's just ignoring me now. Okay. Step 2 is HCl. Got to do step 1 and finish it first. Mechanism will just sneak in underneath here. Shouldn't be too bad. Attack the least hindered carbon. And mechanism in green. We got an IBU. That's isobutyl attached to a carbon that has an O-. And we have a new acetylide attached. An O- in step 2. Picks up a proton. And there you have molecule G with a mechanism. And react molecule G with mercury 2 sulfate and aqueous sulfuric acid. Was this just about predicting the product, Oh, our original asker of the question is not with us now. She perhaps had to go to the same Zoom as the other student.
I'm still here.
Oh, you are still here. Yeah. Oh, there you are.
Yeah.
Your name just wasn't on the screen. Okay.
Oh.
Did you want the mechanism too, or?
Yeah, it was also the mechanism.
Okay, not a problem. Let's do that. So mercury sulfate, we're going to need it drawn out like this. And it will really help if we draw a sulfate ion out like this. Lone pair minus, so it's SO4 2 minus. And we're going to use, what else? We got aqueous sulfuric acid. Going to need some water, some sulfuric acid. And that's a good old chapter 7 reaction where we get an Markovnikov addition of water to an alkene, to a pi. It's an alkyne, really, which puts the OH on the more substituted carbon and the less electronegative mercury on the less substituted carbon. That mercury gets yanked off and replaced with a hydrogen during protonolysis using sulfuric acid, giving us an enol, which will tautomerize to, you guessed it, ketone. So we're going to use a big old R here. And the two black carbons are here. Bottom
Okay, I
one's
think
now a CH3.
that's where my question is, because at some point, sulfuric acid has to take the H off of the OH at some point, right towards the end before tautomerization.
Yep.
And there were two OHs, and I was thinking, do I take the one that's off the end with the I mean, I guess
You're going to
towards the
take
end.
an H off of the oxonium and not a neutral alcohol. We won't be doing neutralize or taking it.
Yeah, it was towards the very end once you take the
Oh, at
mercury off.
the tautomerization step, you're asking. Yes.
Yeah, that's
And
where I
why
was.
take the H off of the OH attached to an alkene versus taking the OH attached to an alcohol? And the answer is the tautomerization wants to make a more stable pi, and there's no pi questions here. There's no need to change the alcohol because there's not a isomer that's more stable. I don't know if that's a great answer, but when we get to the enol, maybe I'll try to remember to bring it up again, and then use the mechanism to answer your question a little more fully. So we're going to start by not protonating. Mercury 2 plus is a stronger Lewis acid than even sulfuric acid is a Bronsted acid. That's how reactive mercury 2 plus is. It loves pi bonds. One arrow there, just one. Mechanism arrows we're doing in green. So let's try to get it down here. We got our new R. It's attached to a black carbon, and it still has a full pi bond. And the other pi bond became this triangle. The two electrons in the pi bond are now in 3 partial bonds to mercury. Mercury used to be 2 plus, now it's 1 plus, with the other second plus shared not quite equally, probably spending more time at the more substituted carbon for hyperconjugation reasons, but we put it in the middle of the triangle and Dr. Whitaker's happy. And I have noticed the student that asked this question, I distinctly remember grading her exams, and she remembered my comment and always put that plus charge a little closer to the more substituted carbon. That kind of stuff makes me happy because that student's paying good attention. That's the oxonium, mercuronium, sorry, and it needs to be attacked. What does it get attacked by? It gets attacked by water. I'm starting to draw the product without having the mechanism. Which carbon spends more time with a plus charge? Oh, we just discussed it. It's the more substituted one. That's where that goes. And we don't have arrows for partial electrons because An arrow is strictly defined as 2 electrons moving. A hook is described as 1 electron moving, and any of these bonds is only like 1/3 of an electron. We don't have a hook or an arrow. So this is something we just don't have a good symbol for. Let's see what we're going to do here. We're going to have a double bond. The OH has to be on one side, and it's an oxonium OH. And the mercury has to be on the other side. I know it looks like it flipped, but it's a backside attack. I'd like to see the O and the mercury on opposite sides of the alkene. And the best base to neutralize this strong acid oxonium is sulfate. And sulfate's got a lot of room to roam here. Let's see what I can do. I'll go with a pink arrow. And that neutralizes the oxonium. Now you have RCCC, mercury plus still over here, and OH here. It's now time to remove the mercury using a strong acid. Also, strong acids have protons. Step is called protonolysis. Good word. Says what it does. I'll redraw the sulfuric acid down here so we see clearly that the the bonding pair between carbon and mercury now becomes a bond between carbon and hydrogen. Mercury lost out in that. It's back to being mercury 2 plus. I don't need to see you draw the side product here, but it's illustrative. And we get sulfate ion. We'll probably use that later. And we have our classic enol. And for the student who had a question earlier, we're going to draw the whole thing out this time because it had an alcohol in there. OH. And what do we have? We have, let's see, we got to draw a double bond and an OH. Let's make sure we have the right number of carbons. Same number of carbons here and here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Good. Now her question was, when we do a tautomerization, which involves removing this H, I'll draw the bond. Why do we remove that H instead of this H? Well, I'm going to take it back to another question first. What is the least stable part of this entire molecule? And you just need to remember one fact. Sigma bonds are more stable than pi. So the least stable part of that molecule is this pi between carbon and carbon. There's no way to use this O to get that pi to be somewhere else involving resonance. They don't resonate with each other. The O can resonate with this pi because it's got a lone pair, or we can use this bonding pair as long as there's some kind of base, but you can't resonate with this pi here. And if we can get this pi to be more stable, we've made the molecule more stable. This guy not being attached can't help the pi. So we're going to use the sulfate ion that we made over here. Look at that, it's right there. And we are going to need a sulfuric acid, another version of it. I'm going to judiciously place it up here. So in terms of the mechanism, this is probably the lead arrow, but I told you can do them all at once. The base in every tautomerization grabs the H, and we will be seeing many tautomerizations this semester. You saw 2 major tautomerizations last semester. You're going to see at least 10 more this semester. So remember, it's always here. I'll go through all the arrows. I don't have them all yet. Base grabs H. That's what bases do, right? Sigma between the H and the O becomes pi. The old pi picks up a proton and becomes in this case, a CH2 becomes a CH3, which is right over here. I'm going to call that, is there a name for that? I don't think I even named that molecule. We'll just call it molecule X. And the result here will become molecule X. And I hope I did a good job on answering your question finally. We'll see. No objections yet.
Yeah, I'm just gonna. So the other alcohol, it wouldn't really matter if it was 1 carbon closer because it needs to be attached to
It
the
has to
alkene
be
as well.
directly attached so that lone pair can resonate in, or any set of electrons on this O can resonate towards the other pi. Yeah, there's way too many bonds in there for that to happen. And now we only have one question. We didn't finish this page, did we? G with mercury. Oh, we did. We did. We even have a mechanism. Was that the end of your questions? I think it was. Save. This must be a blank page then. Yes. Do we have any more questions for today's review? If not, then we'll call it a week. And I know you guys still have work to do. And I emailed you earlier with the study, the week 1 and week 2 schedule. And it is now the format at the end of that schedule is the format for the rest of the semester. So you can start getting comfortable with that. Parts 1 through 6 will not change. So look over the new schedule and see what is ahead of us. I think you definitely have enough work to keep you through next week. And shortly after that, we're going to finish the material for test 1. It'll be in our 3rd week. All right.
So next week is chapter 13, right? It's not chapter 13 and 14.
14 is what I would call a supplemental chapter. It's a review chapter of its own, and it's only done through OWL. I will not be doing any lectures on 14. But if you have any questions about the OWL the 14 at OWL, that would be great for doing these Q&As too. So yeah, the OWLs are due. Look at them, and if you have trouble, we can do some of them together. All right. And then, 13 is the big read, and then 15, 16. Those are the ones you have chapters for in the textbook. All right. So I wish you all a great weekend. And I am off camping as of now. Take care.